I want to talk today about hydride reductions, and the first reaction that I want to look at is the reduction of this compound, this aromatic ketone with sodium borohydride and methanol to produce the corresponding alcohol. And what I want you to remember, what I want you to do is anytime you see NaBH4, sodium borohydride, I want you to think of it as a source of H-. This H- will be attracted to the carbonyl because if we look at the carbonyl, because the oxygen is more electronegative than the carbon will be partially positive, the oxygen will be partially negative. So the hydride, which has a negative charge on it, will attack the partially positive carbon. When it does this, the electrons on between the oxygen and the carbon, the double bond pi electrons go up onto the oxygen, and what we get as a product is this anion with a negative charge on the oxygen, and the hydrogen from the hydride is attached to this carbon right here. Well, the next thing happens is that the methanol provides the second hydrogen, the hydrogen to this oxygen to give us our alcohol. So the oxygen takes this hydrogen, the other oxygen leaves with the extra electrons, and we get our alcohol. If we look at where each of these new hydrogens came from, the one on the carbon came from my hydride, and the one on the oxygen came from my methanol. Now there's another reagent that works a lot like sodium borohydride. It's lithium aluminum hydride. Now the mechanism for lithium aluminum hydride is so much similar to sodium borohydride that I'm not even going to erase any of the structures I've drawn right here. I'm just going to make a few changes. I'm going to replace the sodium borohydride with lithium aluminum hydride. Now the other change that I need to make is that lithium aluminum hydride is a much more reactive reagent than sodium borohydride. If I had a polar protic solvent like methanol around, it would react with that solvent, releasing lots of hydrogen gas and destroying my lithium aluminum hydride. So we usually use ether or some other aprotic solvent as our solvent. But at the end of the reaction, in a second step, we add something like methanol or water to quench the reaction to give us our second hydrogen. So I'll just put ROH. R could be an H and there would be water, it could be a carbon group, it could be an alcohol, but the idea is the same. In the first step, the hydride from lithium aluminum hydride attacks the partially positive carbon of the carbonyl, and then in the second step, after I add my protic source, the oxygen is protonated. Now there are some differences in what you can use lithium aluminum hydride and sodium borohydride for, particularly when it comes to the reduction of esters. If esters are less reactive, so if you try to use sodium borohydride to reduce an ester, most of the time it will just sit there and laugh at you and you'll get no reaction. So you need to use a more reactive reagent like lithium aluminum hydride to reduce these esters. And the reaction we get is a kind of an interesting one, and I want to go through that mechanism. I want you to notice that when we reduce an ester with lithium aluminum hydride, we get an alcohol, just like we did when we reduced the ketone. So let's look at what's happening, and I want you to notice that there are two hydrogens that have been added to this C-double-bond-O, whereas in reducing the ketone we added one hydrogen. So let's look at what's happening, and the reaction starts out exactly the same way. We add a hydride to a C-double-bond-O. The hydride attacks the partially charged carbon, and the electrons go up onto the oxygen just like we did up here, and what we get is this anion right here, which is analogous to the one we got up here when our hydride attached this C-double-bond-O. Now something interesting happens. In the previous reaction we looked at, the reaction stopped there. We added another H and the reaction was over. In this case, the electrons on the oxygen can come back down and the OCH3 can leave. Now OCH3 is not a great leaving group. It's actually a pretty poor leaving group. But the driving force for this is the formation of the C-double-bond-O and the subsequent reduction of the aldehyde that's formed. So let's look at what happens. When the electrons on the oxygen come down and the OCH3 leaves, we're left with this aldehyde. You can see the hydride hydrogen is this one right here. It attacked that carbon. It's there. It's here. We also release a molecule of methoxide. Well, this is a C-double-bond-O, just like this was a C-double-bond-O, and this is a C-double-bond-O, and lithium aluminum hydride loves to react with C-double-bond-Os, carbonyls. So it does a second addition of H to this, of hydride to this carbon. And it reacts the same way it did before. When the hydride comes in, the electrons have to go up. if this hydride came in and we didn't move those electrons up onto the oxygen, we would be drawing something that had 10 electrons around carbon, 5 bonds around carbon, and that is something you do not want to do. So the hydride comes in, the electrons in the oxygen go up. Now, the same thing that happened before happens again in the first example we did. The protic solvent, or it's not a solvent because we're adding it after the reaction is complete. The protic source adds a hydrogen and we end up with our alcohol. And this is our alcohol product with my 2 hydrides added to my carbonyl. You can see that when I have a ketone, or I would do the same thing with an aldehyde, I add 1 hydrogen to a hydride to the carbonyl. When I have something that's a slightly 1 oxidation state higher, and a carboxylic acid derivative, I add 2 hydrides. Hydride 1, hydride 2, and I end up with 2 hydrogens there. Now, this kind of reaction for lithium aluminum hydride, adding 2 hydrides to carboxylic acid derivatives, is not limited to just esters. We can do it for other carboxylic acid derivatives as well. So this is the reaction we just saw, reducing an ester with lithium aluminum hydride, and you add 2 hydrides to the carbonyl, end up with an alcohol. You can also do this reaction with the carboxylic acid. Add 2 hydrides to the carbonyl of the carboxylic acid, you end up with the alcohol. You can also do this with an acid halide, where X is a halogen like chlorine or bromine. Again, you add 2 hydrides to the carbonyl, you end up with your alcohol. You can also do this reaction with an amide. But notice this time the product is the amine, not the alcohol. Now, all of these reactions proceed through essentially the same mechanism as we went through for the ester. The amine is a little bit different because the leaving group is the oxygen derivative, not the nitrogen. But the mechanisms are essentially the same. We add 2 hydrides to my carbonyl carbon.